Within chemical equilibrium, there is an important concept called Le Chatelier's principle, which describes how systems at equilibrium react when external stressors are applied. My name is Alyssa, and this video will help you understand Le Chatelier's principle and how reactions respond to these external stressors. We'll start off with a brief overview of Le Chatelier's principle, and then we'll look specifically at how reactions are affected when we change things like concentration, pressure, and temperature, and how these reactions respond to get back to equilibrium. After watching this video, you will be comfortable with questions relating to Le Chatelier's principle and how reactions readjust to equilibrium under different circumstances. You will be able to answer questions that ask you to use this understanding to determine what effects will benefit reactions as well. First, let's discover what Le Chatelier's principle is. This image shows two bottles, one with N2O4 gas and the other with NO2 gas, two parts of the same reaction, but one bottle favors the reactants and the other favors the products. How can this be? Well, it has to do with how systems shift their equilibrium to relieve any applied stress. Say we were to change the concentration of a product or a reactant by adding or removing this compound. This would cause a shift away from equilibrium, and the system would have to readjust to get back to equilibrium. What about changes in pressure? Again, there will be a shift in equilibrium, and the system will have to readjust. The last change that we will look at in this video is what happens when we change the temperature of a system by either heating or cooling. With a temperature change, the reaction doesn't shift from equilibrium. Equilibrium itself changes, because remember, the equilibrium constant is temperature dependent. First, let's examine what happens if we alter the concentration of species within a reaction. Adding reactants or taking away products will have the same effect on the system. In these cases, we have altered the ratio from equilibrium such that Q is less than K equilibrium, which means that the reaction is proceeding forward more so than in reverse. Let's look at the example of the bicarbonate buffer in our blood. In our muscle tissue, carbon dioxide concentration is high. As more and more CO2, a reactant, is added to the blood buffer, the reaction proceeds in a forward direction to even out the levels of CO2 and reach equilibrium again. What about if we remove reactants or add products? This is of course the opposite situation, and the ratio will again shift from equilibrium, but this time Q will be greater than K equilibrium. This is what happens when we exhale. Our lungs expel carbon dioxide, removing this reactant from the blood buffer equation. In order to compensate for this loss, the reaction shifts towards the reactants to form more CO2 and again reach equilibrium. A handy note to remember for test day is that chemical systems will react by shifting away from added species and towards removed species. Now let's see what happens if we change the pressure or the volume of the system. Take note that only reactions involving gas molecules will be affected by these changes, since solids and liquids are essentially unable to change volume. If we increase the pressure on the system, we can imagine that the vessel containing our reaction is getting smaller. Therefore, the reaction will shift so that the side that has less moles of gas is favored. This relates to the gas law and how the number of moles is directly related to the pressure of the gas in the system. Increasing the pressure causes the reaction to shift so that there is a decreased number of moles of gas and therefore a decreased pressure of the gas. This helps the system reach a new equilibrium. Oppositely, if we were to decrease the pressure and imagine making the vessel larger, the reaction would shift towards the side that has more moles of gas that could fill up this space. This increases the pressure of the gas, and again our system reaches a new equilibrium. Let's look at the chemical reaction that forms ammonia gas. On the reactant side there are 4 moles of gas, whereas on the product side there are only 2 moles of gas. If we were to decrease the volume of the vessel, thereby increasing the pressure on the system, the reaction would shift so that more product was formed and there were less moles of gas present in the reaction. If we were to increase the volume of the vessel and therefore decrease the pressure on the system, the reaction would shift so that equilibrium favored the formation of more reactants since there are more molecules of gas on that side. Lastly, we will investigate temperature changes and how this affects equilibrium. When we change the temperature, the reaction quotient isn't changing like in the previous examples. It is actually the equilibrium constant that changes. Therefore, the reaction needs to shift to reach this new value of K equilibrium. If we increase the temperature at which the reaction occurs, the reaction moves away from the side that has the heat, because heat is considered as either a product or a reactant. Therefore, we can think of temperature like we do concentration to apply Le Chatelier's principle. Remember that adding more of something shifts the reaction away from that side. Decreasing the temperature will then, of course, cause the reaction to shift towards the side of the reaction that has heat. For an endothermic reaction, heat is required in order for the reaction to occur, and so heat is considered a reactant. For an exothermic reaction, heat is released and is therefore considered a product of the reaction. Let's think about that reaction again that produced the two different color gases in the bottles. If we add heat to the reactions shift towards the products, since heat is a reactant, and adding more of it will cause a shift away from that side. If we cool the reaction down, or take heat away, the reaction will shift towards forming reactants, since this reverse process is exothermic and would replace some of the heat that was lost by cooling the reaction down. Now that we are familiar with Le Chatelier's principle, let's do some practice questions on this topic. This question is asking you to think about what factors would benefit this reaction so that it forms more of the desired product. The answer is B, decreasing the temperature. In this equation, heat is a product, and remember, we can think about temperature like we do concentration. Taking away the product will lead to a shift towards forming more product. Therefore, decreasing the temperature would lead to more product formation. Answer choice A is incorrect because increasing the temperature would add products to the reaction, shifting the reaction towards the reactants. Answer choices C and D can both be eliminated because they are essentially the same answer. Increasing the volume of the vessel would decrease the pressure on the system. Furthermore, this reaction has more moles of gas on the reactant side, and decreasing pressure would favor reactant formation. This second question is asking you to think about how we would favor the formation of reactants in this equation. The answer is A. By increasing the pressure, we can form more reactants. In this reaction, there are 2 moles of gas on the reactant side and 3 moles of gas on the product side. To favor the formation of less moles of gas, we need to increase the pressure of the system. Decreasing the pressure, adding SO3, and removing O2 are all examples of how to get the reaction to proceed in a forward direction. Great job if you got those questions correct. In this video, we looked at the different factors that cause reactions to change in order to reach equilibrium once again when an external stressor has been applied to the system. The reaction will shift towards the products in an exothermic reaction if we add either of the reactants A or B, or take away the product C. Increasing the pressure will result in a shift towards the products since there is only 1 mole of gas on that side of the reaction, and decreasing the temperature will form more products since temperature itself is considered a product of the reaction. The reaction will shift towards the reactants if extra product is added, or if reactants are removed from the system. Decreasing the pressure will favor the formation of 2 moles of gas in the reactants, and increasing temperature will drive the reaction away from the formation of heat and towards forming more reactants. Remember to think, shift occurs away from added species and towards removed species in order to answer questions regarding Le Chatelier's principle with confidence on test day. Thanks for watching and good luck studying for your MCAT.